Professor.
Yes. How may I help?
Oh, hi. Did you get my email over the weekend?
I believe so. Let me refresh my memory. No, I did not. I thought I did, but no.
I wrote you on Canvas and email, I believe.
Oh, okay. Did you send me just at W Younger or was it just through Canvas? Because I don't necessarily check the Canvas ones at all.
Both.
Okay. Let me see if I at least see it.
I sent it to both.
Thank you. Oh, yep, I see. There it is. It was filed in a weird place. Yes, don't worry. I've set that date a little bit back anyways, so everything's good.
Okay. Do we need to upload it onto Canvas? Like,
Yeah, if you don't mind, go ahead and do that. Just I use that as my protection from viruses. So yeah, even if you've anybody for that matter, if you've turned in something by email it to me because I closed the box too early or something like that, go back and do that. I set, for instance, the midterm redo. I just set that back. I think I just finished doing that. It should be open now. And anyways, go ahead and submit it that way, even if you email it to me, just because, like I said, I can access it from anywhere if it's in the system as a Canvas turn in assignment. And two, I don't have to download it and, subject myself to potential viruses. So thank you for that. And that's my fault for doing it. Appreciate it.
Oh, that's
Anyone
no
else have any
problem.
questions? Go ahead, Brianna.
Sorry, I have one more.
No problem.
Homework's 11s. Those were
Yeah,
pushed
that's
back
not
too.
new.
Oh, okay.
Yeah, I remember that, guys. If I haven't covered the chapter, no matter what the stupid date says, that's my fault. But yeah, you don't have to cover it. That being said, I know some people panicked and covered it. I will make that right by giving you some extra credit if you spazzed out and did it early. That's fine. I'll try to download that. And now I'll set chapter 11 homeworks back to a normal date. They should be due Wednesday of next week. Maybe the conceptual questions will be due Sunday night, but Tuesday would be the other one, not Wednesday. Sorry about that. So yeah, I'll set chapter 11 and I'll double check we'll skip from chapter 11. We'll jump to relativity. Then we'll jump back to 14. So that means 12 and 13 are skipped. I use those as extra credit because they're worthwhile for you to cover. It's just they're going to be covered in a much more detailed way if you actually happen to be an engineer or scientist in a very particular area. So that's why we don't cover them. But at the same time, I think it's valuable, one, for you to learn how to teach yourself material. So I give you extra credit for doing that. But two, it's not that helpful if you've done it already after I've already covered 14. So anyways, that's why unlike a lot of extra credits, I leave due till the end of the semester. Chapters 12 and 13, I don't leave due to the end of the semester. I actually normally want you to have it done before we go into 14. So those are some extra credits you can do. Anybody else have any other questions? So I will work on this stuff tonight regarding various things that are going on. For instance, the chapter 11, chapter 12, chapter 13, the relativity chapter, which we're going to start after we finish chapter 11. I probably will not even jump into chapter 11 tonight because I realized when I went to my class today for face-to-face, I took the entire time working on the problems related to chapter 10, which was what I thought was going to be a little 5-minute thing. I ended up making it a lot longer. So I'd rather you have a good understanding of chapter 10 than jump into chapter 11. If I remember correctly, I had planned, and hopefully I did it, I planned on making the conceptual homeworks due last night, 11:59 for chapter 10. And then the homework sets, the actual problems as opposed to the conceptual, they're supposed to be due on Tuesday at 11:59 p.m. But someone told me today there was 2 parts and I might have only did one of them. So I'm going to correct that if that's the case. And I'll make sure it's not due till Wednesday. And chapter 11, like I said, will not be due till a week from Wednesday, or a week from Tuesday, I should say. Because remember, I always make it the day before classes start. So you guys are a Monday, Wednesday class, which means your due dates will be Sunday and Tuesday. My Tuesday, Thursday classes, their due dates are Mondays and Wednesdays. So that's why I keep slipping back and forth into saying Monday and Wednesday and Tuesday and Sunday and stuff. So anyone have any other questions that I can thoroughly confuse you over? All right, that's good. Okay, well, we're actually now at 5:20, so technically it's time to start. I have about 12 students in here, which is a small number compared to the whole, but I should really start it. So the last things that we wanted to talk about in chapter 10, there was pretty much two different issues. I sort of alluded to one of them, but didn't really do very much with it. And then the other one I didn't touch at all. But basically, conservation of energy is a thing. That's a whole new thing that we've learned in terms of rotational motion now, that we got to take into account. So I'm going to work a problem that way, maybe two problems. And also, I want to address the idea of rolling without slipping, specifically in the mindset of what frictional force is required to allow such a situation to go. So, for instance, if you take, let's say like a frisbee made out of that nice hard plastic stuff that doesn't have much grip on anything, and if you put that on, say, like smooth linoleum or smooth hard plastic incline, okay, if you just hold that frisbee up and then let it roll down, if the angle's steep enough, what you'll probably find is the frisbee will slide a little bit, and then eventually it'll start trying to roll. But before then, it's just sliding. So it turns out that if you don't have enough static friction, then you can't roll without slipping. It's going to constantly slip, or at least slip initially until it gets up to speed. So that's one of the things that I wanted to address with you guys. So let's start off by looking at a problem where I'm going to allow a sphere to roll down an inclined plane versus sliding without friction down an inclined plane. And then the next thing I'm going to do is I'm going to imagine a series of shapes rolling and sliding down an incline. So let's first off start with the conservation of energy techniques. So anyone have any questions before I move on? All right, I'm going to share screen. Here comes the stupid plugin it's asking me for because it's a new week, obviously. I'm working on it, folks. Hold on. Evidently, I got to download this every week. It's just crazy. All right, now that's available. Okay, now I'm looking here. So what I wanted you guys to realize last time, and I can't remember if I actually wrote it down or just told you about it or what, but the main thing is you've got to know that when an object rolls, there's kinetic energy associated with it sliding down the incline. In other words, sliding without actually rotating. And then there's another kinetic energy associated with rotating. So in fact, the total kinetic energy can often be written as kinetic energy is equal to 1/2 times the mass times the velocity of the center of mass squared, plus the rotational kinetic energy, which is 1/2 times I times omega squared. And remember, this is a continuance of the analogies that we said. So for instance, x in linear motion went to theta, and actually I could say y comma x went to theta. We found that v went to omega. We found that a went to alpha, and time stayed the same, but we did find that mass went to I, and momentum P equals mv. went to went to L equals I omega, RP equals MV, went to L is equal to R cross P. Okay, so it continues that analogy, specifically mass being replaced by I, V being replaced by omega, and you still get the same formula. So that's one of the key things I wanted to point out about the analogy between linear motion and rotational motion. So now what I want to do is imagine an inclined plane. So we're going to draw an inclined plane. And that inclined plane, of course, will have an angle theta. And I'm going to say, in fact, this height is going to be h. And at that height, I'm going to have, let's say, a sphere. And the sphere has a mass big M and a radius big R. And what I want to know is what is V final and omega final. And let's go ahead. Yeah, I'll just I'll go ahead and say this too. I will say V final, omega final, and A equals question mark. Okay. Now I'm going to do part A is going to be sliding without friction. And part B is going to be rolling without slipping. Okay, but that's the three answers we want. We want to find V final, in other words, the velocity of the center of mass in meters per second, omega final, which would be like in radians per second or something like that. And I'd like to know the acceleration, which we can get from Newton's second law, or we can use it kinematically. So I'm going to use conservation of energy methods. I'm going to say solution. So in rolling without slipping, I'm still going to use conservation of energy, but my conservation of energy, the way I taught you guys, was work in plus U initial plus kinetic energy initial is equal to work out plus U final plus kinetic energy final plus E loss. And of course, I've talked to you ad nauseum about all the different things that these terms could be. But in this particular case, I'm basically ignoring the idea of energy loss. So even when I do rolling without slipping, it's going to turn out that that work done by that friction force in causing the rotation, that can't actually do any work because it's going to be, in fact, perpendicular to the motion. So that doesn't add any energy. So in this case, we're going to have this is 0. We're going to have this is 0, and we're going to have this is 0. And this basically just reduces to the normal Giancoli / Survey / Holiday resonant conservation of energy equation, which is U final plus U initial equals, or excuse me, U initial plus kinetic energy initial equals U final plus kinetic energy final. So we've got that. Now I'm also going to take the idea that to the bottom edge of this sphere, say, is a height h, but to its center of mass is a height h plus r. And in fact, when it rolls down to the bottom, it'll go from a height h plus r to a height of r. So why not just call the 0 level to be just a height h above the basically lowest level? So what that's going to mean is I'm going to let the ball fall with initial velocity of 0. So that's going to equal 0. And I am going to let it bottom out at a energy of 0. because I'm basically saying that when the ball is this height, I can write it like this, for instance. This is h plus r, and this is just plain r. So I can say this height right here is u equal, well, actually, this not write it that way. That looks really horrible. This height right here corresponds to u equals 0. So now all I have for part A is just m times g times h is equal to, now remember, it's sliding without friction, so it can't rotate at all. The only kinetic energy I'm going to have is therefore 1/2, oops, wrong m, 1/2 mv squared, and this is the v final that we're looking for. You can see automatically that the mass cancels out, and in fact, we're going to get v final equals the square root of 2 times g times h. Now, in the case of a mega final,
Wait,
it's not.
Professor, I'm sorry, I didn't see where you got the MGH from.
Okay, that's our potential energy formula. U is equal to m times g times the height.
Okay.
So the way I did that originally was I calculated the work done in lifting an object, but I imagined the object where I was just applying enough force where it counteracted gravity, and then I allowed like a random molecule to bounce against it to cause it to go up. So that way I wasn't putting any energy into speeding it up. I was just putting energy into lifting it. So when I did that, I ended up getting that the work done was m times g times h. Okay. Now, since this sliding without friction, then the angular velocity is 0. And if we go on the assumption that that a is a constant, and there's some value to this, so I'll say, assuming then v squared final is equal to v squared initial plus 2 times a times x minus x0. Well, I think you can see if this triangle has a height h and an angle theta, then we can say that, for instance, sine theta is equal to opposite, which is h, over hypotenuse, which is what I'm going to call x, like that. And then I'll call, of course, x0. I'll just call that 0. And I can see that, in fact, x is just going to be h over sine theta. This is going to be 0 as well. So I can find that with this answer, a, again, assuming a really is a constant, so that kinematic equation will work, I'm going to say that a is going to be v final squared over 2 times h over sine theta, or putting in what v is, that's going to be 2 times g times h times sine theta over 2 times h. And we can see in this case that the h's cancel out and the 2's cancel out, and I'll find that a is in fact just g sine theta, which we might have remembered that anyways, just from the fact that we had done inclined planes before, and we knew that the answer was g sine theta for an inclined plane with no friction. So here's our answers for part A. Any questions on that?
I didn't see, like, I was writing still, so I didn't see how you went from the equation to a equals vf squared over 2a.
Okay, that's cool. Not a problem. You see the equation that I wrote? Vf squared equals v0 squared plus 2a.
Yeah.
Okay,
Yeah.
so that V final is what I just calculated in the red box above it. So we know that V final is the square root of 2GH. Right now, though, I'm solving that blue equation for A. So I think you can see that it'd be V final squared over 2 times X minus X0. But the X minus X0 is in fact just the what I called L or what I called X earlier. And X we see was equal to H over sine theta. So that's why I put H over sine theta in the denominator here. Now, when I substitute VF, which is the square root of 2GH, once I put that in there, it's squared. So it's just going to come 2GH on top. So that's why the 2GH is to the right of the second equals on that last line for the acceleration. So that's where the 2GH came from. But there was also a 2 in the denominator, and there was a H over sine theta in the denominator. So the sine theta came to the numerator, and the H stayed in the denominator. So those canceled out. Now, do you see where that came from?
Yep.
Okay. Good job. Make sure y'all, yeah, if y'all miss stuff like that, that's totally what you were supposed to do. All right. So we've got B now, and the difference is here. So when I say something's rolling without slipping, you could imagine, let's say the sphere rolling a distance of 3 inches. Well, what that means is imagine you had painted the outer edges of that sphere with some wet paint that's say blue or something. Now, when it rolls 3 inches, what would happen since it rolls without slipping, exactly 3 inches of paint would be jacked up on the surface of the sphere. If, in fact, less than 3 inches was janked up, then that would mean that it didn't roll without slipping. It clearly slipped a little bit. So what that tells us is the arc length around has to be equal to the distance traveled. And if you take the arc length around, and divide it by the time taken, you actually get the velocity. So the actual thing that occurs as a result of this is that S is equal to, since our radius is big R, S is equal to R times theta becomes S over T is equal to R times theta over T, or you can look at it this way, ds over dt is equal to R d theta over dt. But in either case, you end up getting V equals R omega for rolling without slipping. And in fact, you could go further and say, let's make this right. A is equal to R times alpha. So this, and this are all 3 conditions that could be true as a result of rolling without slipping. Does everybody follow that? Anybody have any questions about that? All right, now that I have that, I'm going to do conservation of energy again. And just like last time, work in is going to be 0, initial kinetic energy is going to be 0, work out is going to be 0, U final I'm going to assume to be 0, and then all I have left is K final because E loss is also 0. So the left-hand side in this case is just going to become M times G times H. But the right-hand side, because it's rolling, we're going to have a 1/2 M V final squared plus 1/2 I omega final squared. Now, we can also realize that this seems bad because it looks like mass, the result's going to depend on mass, which clearly was not the case before. So how are we going to make this adjustment? Well, what I know is that the ice for a sphere is equal to 2/5 mr squared. And I had a student ask me about this. So if you guys have tried to actually go and do the calculus to find the moment of inertia of a sphere, and you keep getting 4/5 mr squared, that's because it's really hard to do for a sphere unless you either do some really kind of complicated differential mass element, or two, you actually use a double or triple integral. And you're not really supposed to be at that point in your calculus course yet. So it's perfectly fine that you can't do it. But the main thing is the radius that you using in the integral of r squared dm, that is not just r, the radius of the sphere. That's going to be r, but only the component of r that's parallel to, or excuse me, perpendicular to the rotation axis. So if you're getting 4/5, that's where the result screwed up. That being said, I don't specifically require you to do a sphere. If you want to make sure you can do the calculus that's necessary to solve for moment of inertia, then I want you to do that. And the things that I expect of you are the moment of inertia for a rod spinning about its end, the moment of inertia for a rod spinning about its center of mass, both of which are uniform masses, and the moment of inertia of a cylinder, whether it be a flat cylindrical disc or an actual thick cylinder, or a hollow cylinder where it has an inner radius and outer radius. All of those are fair game. And I might even say that the rod could have a non-uniform density. I might have, say, the density is mass per unit length, and that's actually proportional to x, or proportional to x squared, or proportional to x cubed, or something weird like that. I could actually do that. But other than that, I'm not requiring you to know the calculus to find the center of mass, or excuse me, the moment of inertia of such a thing. All right, so now that I have that, and I also have v equals r omega, I can change this equation to m times g times h is equal to 1/2 m times v final squared plus 1/2 times 2/5 mr squared times, here's where I'm using v equals r omega. This is going to be v final over r, and that's going to be squared. So hopefully you can now see that the masses do in fact, or the single mass does in fact cancel out, and the radius r cancels out as well, because it's r in the bottom and that whole thing's squared. So what I'm getting here is basically independent of mass and independent of radius. In fact, you can see that I'm going to have 1/2 v final squared plus 1/5 v final squared. That in fact has a least common denominator of 10. So that'd be GH. I'm going to write this over here. GH. Oops. Go back to black. So that's going to be G times H is equal to 5/10 plus 2/10 times V final squared. So V final is equal to the square root of, in this case, it's going to be 10/7 GH. Oh, I forgot I used a capital H. Hold on. So that's the answer for part B, or one of the answers for part B. Now, of course, I also need omega, and omega is V over R. So you could also write omega final is equal to the square root of 10 GH over R squared. Because if you actually take that R and multiply it out front, if you want it inside, you're going to have to square it to get there. So that's another answer. And again, if we go on the assumption that the acceleration is a constant, then we can use that same kinematic equation, v squared equals v0 squared plus 2 times A times the length. Well, in this case, we're going to get A is equal to, working this out, we should have what, 10/7 GH divided by 2, that'd be 5/7. Yeah, that'd be 5/7, and then divided by H over sine theta. So that would be 5/7 G sine theta. And yes, so I think this is going to be 5/7 G sine theta. Now, I was working that algebra out in my head, so I would really encourage you all to check my work and let me know if I got that wrong. But that's roughly off the top of my head, that seems to be right. Basically, all you have to do is, of course, plug it in the v squared equals v0 squared plus 2a x minus x0. The x minus x0 is just going to be h over sine theta. So on the other side, that becomes sine theta over h. And then, yeah, so that looks right. Notice it is different, though, from the actual A that I got for just the inclined plane. Speaking of which, I'm going to make this a little prettier because this turned out bad. That fraction looked rough. So I'm again saying this is 5 and this is 7th G sine theta. Any questions on that? Feel free to work out the algebra in between, but that should be the answer. Notice the acceleration is not as big. Before, the acceleration was G sine theta. This is only 5/7 of G sine theta, and a seventh's about 14.28%. You can probably guess why I happen to have that memorized. So we're looking at about 29% lower acceleration as a result of rolling without slipping. And the reason that is, as you can see from the conservation of energy equation, essentially rolling without slipping locks down the ratio of the center of mass kinetic energy to the rotational kinetic energy. And that ratio fixes that some quantity of the total energy that it has is going to be spent on the rotational kinetic energy. So that's stuff that would have otherwise been used to just make it speed up, like if I did in part A with the sliding without friction, just by, oiling up the surface and making it really smooth. So any questions on that? Okay, well, let's go ahead to the next thing where I'm going to imagine a series of objects rolling down an incline and or sliding down an incline. So what I'm first going to do is I'm going to imagine an incline like this. And let's say the angle is theta. Let's say this height right here again is just h. And we can pretend we know theta and h, for instance. But up here at the top, I'm going to put a sphere of mass m and radius r. But I'm also going to put a something like a wedding band, say. So I'll just say a wedding band. And this could be a mass m and a radius r. And I'm going to put a cylinder. And this one's going to be, let's say, M2 R2. And so I got a wedding band, a sphere, a cylinder. I'm going to also say there's going to be a sphere sliding without friction. And there's also going to be a soup can. And of course, it's going to have a mass M3 and a radius R3. Okay. What I want to know is which one reaches the bottom first. And then I'm going to say second. And then dot, dot, dot. In other words, I want to put them in order. Okay. Everybody understand what we're doing here? So let's start off with the sphere. All of them are going to start off with conservation of energy. So I'm going to say solution. Wn plus potential energy initial plus kinetic energy initial equals W out plus potential energy final plus kinetic energy final plus E loss. Okay. And in these cases, I'm going to say that's 0. I'm going to say that's 0. I'm going to say that's 0. I'm going to say that this is 0. And I'm going to say that this is 0. So first off, let's work on the sphere. So in the sphere case, I've got MGH is equal to 1/2 MV final squared plus 1/2 I omega squared. And these are all other than the one that's sliding without friction. So rolls. Oh, that's bad looking. Without slipping. Okay. So in this case, this is going to become MGH is equal to 1/2 MV final squared plus 1/2 2/5 MR squared V final over R quantity squared. So we already know basically from the previous one exactly what the deal is. V final should be equal to the square root of 10/7 GH. Now, by the way, if you assume the acceleration is behaving in a fairly normal way, or in fact that it's constant, which we can't see right now, but it will be, then your kinematic equations apply. But not only that, what that means is the one with the final velocity should have a higher velocity at each point other than against, say the sliding one, which, that's going to be a different scenario. But the main thing is the final velocity is indicative of how long it took. So for instance, a one with a really high velocity would take the least amount of time, and the one with the lowest final velocity would take the most amount of time. So by calculating the final velocity, I am doing the same thing as determining how quick or how long it takes to get down the inclined plane. Just high velocity means it's going to take a little time, and low velocity means it's going to take a lot of time. So we got that. We don't know how that compares to the other ones yet because we haven't figured out the other answers, but that we do have. So we have that for the sphere. Now I'm going to do for the wedding band. Now the deal with the wedding band is that basically it's sort of like a bicycle rim with no spokes and no hub. You just have basically the ring around the outside. Well, the nature of that is the ring is very, very thin compared to the radius. So essentially all of the mass is out at a distance R. And that's sort of your worst case scenario. remember the integral is equal to r squared dm. If you put all the mass at a distance big R away, then all the mass is going to be reluctant to rotate. But that being said, we'll go ahead and write it down. We're going to say m times g. Well, actually, I should stick to the fact that I use different masses for each of these. I was just trying to show you, in fact, that the masses really didn't matter. That's why I wanted to give a different mass to each one. So for this one, it's going to be little m times g times h is equal to 1/2 mv final squared plus 1/2 I omega squared. But I for a wedding band is just m, oops, wrong m again, is just lowercase m, lowercase r squared. And then, of course, omega is going to be v final over lowercase r, and that's going to be squared as well. So I think you can see that the r's are going to cancel out with that one. All the m's are going to cancel out. And in fact, I'm going to get v final is equal to, notice in this case, I'm going to get 1/2 v final squared plus 1/2 v final squared. That's in fact 2/2 are just v final squared is equal to mgh. So, or excuse me, is equal to gh. So v is equal to the square root of g times h. Which obviously 1 is not quite as big as 10/7, which 10/7 is about 1.43 roughly. So we know that's a little smaller. So I'll say this one's in fact a smaller velocity than v final, or I'll just say it this way, than the square root of 10/7 gh. So we already know that the sphere will make it down faster than the wedding band, but you should expect that. Like all the mass is really as far away from the radius as from the axis as it can be. So that sucker should go kind of slow. Now I'm going to do the next one, which is the cylinder. So again, in this case, it's m2. So I'm going to have m2 times g times h is equal to 1/2 m2 v final squared plus 1/2. Now for a cylinder, I know the moment of inertia is 1/2 m r squared. And then of course, the angular velocity is going to be v final over r2. Of course, that whole thing is going to be squared as well. So I'm going to have 1/2 plus 1/4 on the other side. So that's 3/4. So I'm going to get v final. I'm going to get v final for this guy is actually equal to square root 4/3 gh. Now, this is essentially the square root of 1.33 gh. And this one was essentially the square root of 1.43 gh. So you can see this one's actually a little smaller than 10/7, but not quite as big as, but not quite as small as gh. So now we're looking at, I'll write in a different color so we can keep up with it. Now we're looking at the square root of gh is less than the square root of 4/3 gh, which is less than the square root of 10/7 gh, because that one's of course 1.43, the other one's 1.33, so on and so forth. Any questions on that one so far? Now for the sphere that's sliding without slipping, I think I heard somebody say something. Did you have a question?
I was looking at the wedding band one really fast, and I overlooked. How come you didn't put the 2/5 in front of the MR squared? Is that because it's not spherical? It's only a circle.
Yeah, exactly. The formula for a cylinder is 1/2 mr squared. The formula for a sphere is 2/5 mr squared. And for instance, the formula for a rod is 1/12 or 1/3, depending on whether you're doing it in the center or at the end. So yeah, I am making use of those formulas.
Okay.
And they're, by the way, they're like in a table within your book, and you can in fact expect to have those like on your final exam, unless I specifically ask you, which I might, by the way, to calculate the moment of inertia of a rod. Maybe I won't give you the rod formula because I expect you to know it, but normally I don't do that sort of thing. I still give you the moment of inertia formulas. Okay.
Okay.
All right, so now I've done the everything but the sphere sliding without friction in the soup can. I'm going to do the soup can next. The soup can is kind of interesting, and the reason why I like it is because the soup can, notice, really looks like this, where the vast majority of its mass is out at a radius r, because it's all the metal on the sides is all way out there at a radius r. Now you then have a little bit of metal at the very bottom, which is distributed from r equals 0 to r equals r. But the main thing is, because most of your mass is out there, this actually is a little bit easier to rotate than the wedding band. So slightly smaller I than wedding band. Okay, the wedding band was mr squared, so we might say I soup can is on the order of the square root of, let's say, 0.98, say, GH. Just making it up, just realizing that it's in fact going to be less than 1, but not necessarily a huge amount less than 1. The main thing is the fact that we know it's less than 1 means that the final velocity is in, or excuse me, I wrote something errantly here, and now my eraser is not working. I is going to be on the order of 0.98, say, M3 R3 squared, which, by the way, is less than I wedding band. Okay. So we've got that one. That means our velocity final should be slightly faster than the velocity final for the wedding band, which is really our slowest so far. Okay. Now, I've got to do the final part, which is in fact the sphere sliding without friction. And so sphere, and it really doesn't matter what shape it is, to be honest with you. The main thing is the fact that it's sliding without slipping, or excuse me, without friction. in that case, you're going to get, for this guy, I'll say it is M2 GH is equal to 1/2 M2 V final squared. And of course, that's going to give me V final equals the square root of 2 times G times H. So that's in fact going to be the fastest. So from shortest time to fastest speed, we're going to say the fastest one we found so far is the square root of 2GH, which is greater than, now the next biggest one, 2GH is definitely bigger than 4/3, is definitely bigger than 10/7. So what's actually closer to it? Well, we know that the can is going to be moderately, the soup can is going to be moderately faster than the wetting band, but the wetting band is the slowest. Okay. So 2GH is the fastest. That's the object sliding down the incline. And then the next fastest will be the sphere. And then the next fastest will be the cylinder, which is square root, which is the square root of 4/3 GH. And then the next thing, 4GH, the next thing is, I've got 4/3, I've got, okay. That's sliding, that's this, that's that. We already did 4/3. So I checked that one. I did 10/7. I did that one. Oh, the wetting band was GH. So then I've got the soup can. And then I've got the square root of GH, which is the wetting band. So we can see if I write this, let's make it like this so it's big enough to say something. I'm going to say this one is the wetting band. This one's the soup can, which SC should represent that enough. The square root of 4/3 GH was what we got for the cylinder. So this one's going to be the cylinder. And this one's going to be 10/7, and the 10/7 was what we got for the sphere. So I'm going to put down here sphere. And then over here, I'm just going to put sliding. So obviously the fastest thing is sliding. The next fastest is the sphere. The next fastest is the cylinder. And the next fastest is the soup can. And then the slowest is the wetting band. Any questions on that? I'm going to zoom into this again since I had to write it so small for it to fit in there, just so everybody on the video can see it. We see the fastest is, of course, the sliding. Then the sphere is the second fastest, then the cylinder, then the soup can, then the wetting band. Any questions? All right. Well, there's one more really big problem that I want to make sure you guys can do and can understand. And this is basically me trying to calculate what is the necessary friction force for something to roll without slipping. Okay. So I'm going to start again with an object. Now, your book does this, I want to say for a sphere. What I'm going to do is I'm going to do it for an arbitrary thing. So it'll actually give you, in fact, another example other than the book gave you. So what we can find, for instance, is that in general, on that table, the moments of inertia are always some number, which I'll call, say, big N, times M times R squared. For instance, for a sphere, then N was equal to 2/5. For a cylinder, N was equal to 1/2, and so on and so forth, right? So I'll put dot, dot, dot. So I'm just going to treat an arbitrary object whose moment of inertia is some number N times mr squared. So what I want to know is what is the necessary static friction for an object to roll down an incline without slipping. Assume I is equal to some number N times mr squared. Okay. So I'm going to take and say, this is my solution. And I'm going to start off by drawing an inclined plane. And this is going to be an angle theta. This will be a height h. And of course, we could get the length if we really need to. So what I'm going to do this time is I'm actually going to do it with conservation, or excuse me, with Newton's second law of motion. So right here, for instance, I'm going to imagine that it has some velocity v at this particular location. And I'm going to say that this is an object of mass m and radius r. And at this point in time, it's moving with a velocity v. And the forces acting on it, of course, are the weight, which is mg. I'm going to draw the normal force this way, which is Fn. And I'm going to draw another force this way, which is the friction force. And friction force, by the way, is always less than or equal to mu static times the normal force. If I actually find out that the friction force needed is greater than mu static times the normal force, then I know it's going to roll with slipping as opposed to rolling without slipping. So now I'm going to draw a coordinate system, a free body diagram on a alternate coordinate system. So let me start off by drawing a tilted coordinate system. That's going to be my y prime axis. This is going to be my x prime axis. Okay. The object, in fact, is going to look like this, roughly. Okay. I can see I have a force that's actually acting in the positive direction. And the positive direction I'm going to indicate by a green arrow. And that just means this is actually a part of the diagram where the vector is already consistent with the units. And in fact, that force is the normal force. Now there's another force acting. And this one, of course, is acting essentially on the center of mass. That force does not, in fact, is not been converted to this coordinate system. So I'm going to leave it in black, and really it should be drawn right there. And that's mg. Of course, this angle right here is theta. So that means this angle right here is theta as well. And we have a negative y component. Oops, I drew it a little long. That doesn't look so bad that way. Okay. So that's a negative y component, which is in fact mg cosine theta. And in fact, we also have a positive x component. And that one's going to be mg sine theta. And there's also going to be another negative force. And that one's already computed parallel to an axis, so that's F. So now we can forget about all the vectors that are black. The only ones that matter are the ones that are now colored either red or green, green being in the positive direction and X being and red being in the negative direction. So let's start off with the summation of, actually, I should do a different color. Let's start off with the summation of the forces in the x direction is equal to mass times acceleration in the x direction. That's actually going to turn out to be the only acceleration, so I'm not really going to subscript it when I actually use it. But right now, we can see that the forces are mg sine theta minus a friction force, and that's all equal to m times a. I'm going to call that equation 1. Everybody agree with that equation 1? I didn't leave off anything, did I? Now I'm going to treat the summation of the forces in the y, and technically I've been calling these primes, so I should have put little prime marks up there. So I'm doing it now. So the summation of forces in the y prime direction is equal to mass times acceleration in the y prime direction. And in fact, we do not expect this ball to be bouncing perpendicular to the plane. So in fact, that y prime should really, the acceleration in the y prime direction should really be 0. So in this case, I'm going to get mg, or excuse me, Fn minus mg cosine theta is equal to 0, which I can just say, oh, that's actually giving me the normal force, which is obviously mg cosine theta, and I'll call that equation 2. So just to keep track, I'm going to underline the things we don't know. We do not know F. We do not know A. And technically, we didn't know F normal until just then. So that's 3 unknowns so far. Now I also have a torque equation, which basically says the summation of the torques is equal to I times alpha. I want you all to make sure you read your book. Your author takes the time to tell you when this equation can be used. That's an important concept to understand. He mentions, for instance, when the axis of rotation it points in a constant direction, that's a case that works. And another case that works is when the axis of rotation is through the center of mass. So he gives you some more details on that, but that's definitely something you should know. What I'm going to do is try to make a coordinate system that's consistent, or excuse me, a sign system that's consistent with the coordinate system. So what I have right now is anything going in the positive y prime direction or the positive x prime direction is a positive quantity. So since I see that the friction force tends to rotate that body, that roundish thing whose geometry we don't know, in the clockwise direction, that's exactly the same direction it has to rotate to go down the incline, which I called the positive direction. So I'm going to call that a positive torque. And in fact, if you look at it, you can see there's a lever arm vector that points from the center of the circle to where the script F friction force is acting. And that is in fact perpendicular to the force script F, the friction force. So torque is equal to R cross F, basically just becomes R times F. So that is a positive torque. And in fact, you see that the mg, which actually acts on the center of mass, that has no lever arm. Therefore, the torque due to that one is 0. And similarly, the normal force, which actually points right through the center of mass, that also has 0 lever arm. So we literally only have one torque, and that torque is going to be lowercase r times the friction force, and that's equal to the moment of inertia, which we said was N times M times R squared, and then that times alpha, which we can write, if we assume it's rolling without slipping, we can write as A over R. So that's that third condition that I showed you in the previous problem for rolling without slipping. It was this guy. It was this guy. And it was this guy. So those are the three conditions for rolling without slipping. Now that we have that, you can see what's going to happen is this R will cancel out with one of these, but this R is going to cancel out with the other one. So in fact, I can see that the friction force is just going to be N times M times A. And I'm going to call this equation 3. Now, the friction force is definitely an unknown. The acceleration A is unknown. Of course, we also had alpha. Alpha was an unknown. So, for instance, I can mark that like I did before with a line under there, just to remind us it's an unknown. And I've already used the other equation, which was A. Let me write it in the right color, which was A is equal to R times alpha. And that could be equation 4, for instance. So I can actually say this is an unknown as well. So you see, we actually did have 4 unknowns, and we in fact needed 4 equations. The unknowns were the normal force, the friction force, the angular acceleration alpha, and the regular acceleration A. So that's 4 unknowns, 4 equations. I've already plugged 4 into the torque equation so that I could get equation 3. But now I'm going to take equation 3 and put it in equation 1. So let's say plug 3 into 1, this is going to give me mg sine theta minus n times m times a. Well, that's supposed to be an n, and I just made it an m. So n times m times a is equal to m times a. So I can ultimately say that this is going to be, notice there's a common factor of m, so I can get rid of that, which is good because that means the answer is not going to depend on math, which is sort of what we learned from Galileo, hopefully. So when I pull the a to the right-hand side, it's going to become n plus 1 times a. So a is in fact going to be equal to g sine theta over n plus 1. I will circle this as if it's a final answer, which it actually is. Any questions on that one so far? So now I've got it in terms of n for any arbitrary object. Now we can use that, for instance, to see for a sphere, n was 2/5. So if I take 2/5 and add to it 5/5, which is what's in the bottom, I get 7/5, which becomes 5 over 7 times g sine theta, which is what I got down here in the bottom right, 5/7 g sine theta. So that's completely consistent with my work before. That makes me feel good. What about the 10 when I got the, no, I don't need that. That's the only one where I calculated the acceleration. So I guess that's the only one we can compare it to. But I've done that. Now I can go ahead and find out what the angular acceleration is. Of course, A is equal to R times alpha. So alpha, dang it, alpha is equal to A over R. So we can actually say alpha is going to be equal to G sine theta over R times n plus 1. And that gives me the angular acceleration, which is something else we could have found. I didn't actually ask for it. All I really cared about was what the friction force was. But now I found A and alpha. The friction force, now that we know A, we can say the friction force F, which we found was what? From equation 3, it was N times M times A. That's equal to N times M.
Sorry. Like vibrating, but echo.
G sine theta.
Is your mic on?
Yeah, it is. Your mic's on. N plus 1. Okay, so now we can go ahead and write that the friction force F is going to be N over N plus 1 times M G sine theta. Any questions on that? Now, remember the biggest F, or the biggest that a friction force can be, a static friction force, is mu static times the normal force. And we already know what the normal force is. The normal force is mg cosine theta. So this says that mu, or excuse me, that F static max is equal to mu sub S times M times G times cosine theta. If that's the case, then you can compare that mu S times M times G times cosine theta to N times N plus 1 mg sine theta. And that could actually help you determine it. You could actually solve for mu S as well and see what mu S would have to be. Mu S, for instance, would have to be the friction force divided by mg cosine theta. So sine theta over cosine theta, that would mean that F would be equal to, well, actually looking at it that way, I don't want to, I'd say mu S would equal N over N plus 1 times tangent theta. So I'd say mu S is equal to N over N plus 1 times tangent theta. And the reason we got that was because sine over cosine is in fact tangent. Any questions on that? All right, so now you've been shown how to use that torque equals I times alpha equation to actually find the friction necessary to do rolling without slipping. In fact, let me turn down to this. I want to read out that part about the using tau is equal to I times the center, I times alpha. So here's what it actually says. It says, be careful, however, do not assume that the summation of the torques is equal to I times alpha is always valid. I'm looking at section 10-9-4 in your textbook, 10-9-4. It says you cannot just calculate tau, I, and alpha about any axis unless the axis is one, fixed in an inertial reference frame. So if the rotation axis is not accelerating, basically, and it's fixed in that in that inertial reference frame, again, not a accelerating reference frame, then you can use that. Or two, it's fixed in direction but passes through the center of mass of the object. So as long as the rotation axis passes through the center of mass of the object and is in a fixed direction, then you can use it even if it's accelerating, if the axis is accelerating as it goes down an inclined plane, for instance. So that's perfectly fair. Any questions on that? Now I'm looking at an example that your book worked out, and your book worked out basically for analyze a rolling sphere of example 1017 and figure 1034 in terms of forces and torques, and determine the velocity v center of mass of the sphere's center of mass at the base of the incline and the magnitude of the friction force. So that's one of the examples, is example 1019 that the book works. I just did sort of the equivalent, but one for an arbitrary shape, because I am not going to put in, like this one did, a rolling sphere has I equal to 2/5 mr squared. So what I called capital N was 2/5 in this case. Now, when they did that, they ended up getting that the friction force had to be 2/7 mg sine theta. So if what I worked out was correct, then that should be N, which is 2/5, over N plus 1, which is 2/5 plus 1, times mg sine theta. And if that turns out to be 2/7 mg sine theta, that further confirms that what I did was correct, didn't make any careless mistakes. So if I take the bottom part, n times n plus 1, or excuse me, n over n plus 1, if I take the bottom part, n plus 1, that's 2/5 plus 5/5 is obviously 2/5 plus 5/5 is obviously 7/5. And then I divide 2/5 by 7/5. That's going to be 2/5 times 5/7. So the fives are going to cancel out and I'll get 2/7. And sure enough, 2/7 is exactly the answer that your book has in example 10-9 or 10-19. Yeah. So that does give us a consistent answer. 2/7 is the same thing as n over n plus 1. So I'm quite confident about that. Any questions? By the way, it says in the bottom of that example, it says, note, if the coefficient of static friction is sufficiently small, or theta sufficiently large, so this equation gives the friction force is greater than mu static times the normal force, the sphere will not simply roll, but will also slip as it moves down the plane, because F friction equals 2/5 mg, or excuse me, 2/7 mg sine theta, and mu static times the normal force is supposed to be mu static times mg cosine theta, then the friction force is greater than mu static times Fn is equivalent to saying tangent theta is greater than 7/2 mu sub s. So if I take and solve for tangent theta in the expression that I've got here in the bottom right, then tangent theta would equal mu sub s times n plus 1 over n. So we're seeing in this case, in fact, 7/2 US. So that's again consistent with what the book did. Any questions on that? All right, so we're done. The class is supposed to be done at 7:40. It's 7:36. I've certainly kept y'all plenty of times late. So you're certainly free to go. I will wait for the last person to leave. I will be posting these notes immediately. And as soon as the video finishes downloading, I'll be posting that to my YouTube channel so you can catch that as well. Over time, I will edit out the first part, which is, where I'm talking to you guys before class starts and stuff like that. But initially, it's going to show that too. So everybody have a good evening. Make sure you go ahead and turn in your midterm redo if you haven't already. If you've emailed it to me, still turn it in the appropriate place. I'm going to make sure that it's open so that you can still turn it in. Until I actually start to grade it, I'm probably not even going to take off any points for it being late. So just get it in as soon as you can. That way you won't lose any points. So even if you emailed it to me, I still need you to go into module, I think it's module week 10, and I'll still need you to go in there into that module and turn it in where it says midterm redo. And it should be a PDF, of course. Have a good one, everybody. And as I said, I'll wait for the last person to leave before I go, but I'll see you next time. I really should write this n plus 1 a little clearer. That looks like n times h. I'm going to fix that right quick. Anyone, Greg or Diana, have any questions? Diana, no questions? All right, I'm going to stop sharing and then I am going to Oh, okay. I see you posted a question down. As I couldn't figure out one of the questions for the midterm redo, is there a way I could get an explanation for it? I turned it in already. Yes. Do you recall which question it was, Diana, or can you share me share a photo of it? I'll be glad to help you. I would suspect it's probably the one where you had a spherical shell and they ask you for the gravitational acceleration. That's one that a lot of students were having a hard time with. Was that the one you were asking about, maybe? Diana. Oh, there it is. Okay. So it's the one with the equation for force given by F equals 4 newtons I hat, or 4 newtons X times I hat, and 2 newtons n times y times x. What are we meaning by that? Is there supposed to be a j hat after that or something? So it is supposed to be a j hat. So so if the equation of force is given by that, were they asking for the acceleration, or were they asking for potential energy? What were they asking for? I don't remember it off the top of my head. In other words, actually, let me see if I can pull it up. That might help. Yeah, I'll do that. Still working on it. They're asking for the work done. Okay. And the work done and going from a particular X value to a particular X value, or a particular XY value to a particular XY value. All right. So what I'm going to do is I'm going to look in the actual midterm, which I see is right here. Let's see if I can find that problem. So it's not that one. It's not that one. I'll get there. Don't worry. Not that one. Ah, I see it now. Okay, and I see why. It's got an X and a Y in it. So a force is dependent on position and is given by 4 newtons per meter xi hat. So what they're saying is F of x comma y is equal to 4.00 newtons per meter times x times I hat plus 2.0. I'm going to go ahead and call it 2.00, even though it didn't list it that way, newtons per meter squared times x times y in this case times j hat. Oop. Yeah, that's a j hat. And they want to know how much work is done. A force is dependent on position and object begins at the origin. So work from x initial y initial is equal to 0, 0 to x final y final is equal to 1.00 meters, comma 0.00 meters y. Okay, so work is equal to the integral of f dot dl. If I draw the coordinate system right now, that's a worthwhile thing to do. There's my x-axis. This will be my y-axis. And in fact, I'm going to be going from this spot right here to the spot x equals 1, y equals 0. So I will mark this as if it's 1/2. And then this, of course, is 3/4. So this would be 1 right here. And that'll be my final spot. And obviously, there's a bunch of different paths I can take. I'm going to say I took this line straight from here. Now, if it's a conservative force, it shouldn't matter what path we follow. And in fact, what I'm going to say is this little chunk right here, dl, is going to be dx I hat. Okay. So I can now say f is equal to the integral of, now I'm going to drop the units for a second here and just say 4x I hat plus 2x y j hat. That's all dotted with dx I hat. Now here's the problem. This is a path integral or a line integral. So in order to make it a actual path or line integral, I've got to make sure my variables x and y behave like they're actually on the path that I chose. So if you'll notice on the path that I chose, on this path, y is equal to 0. So work becomes equal to the integral of 4x I hat plus 0 j hat, which is just going to be 0, but I wanted to show you what's happening to it, dot dx I hat like that, which actually didn't matter too much anyways, because the dl that I chose was actually in the I direction anyways. So this is going to be an integral of the 4x just comes out in front, and then I get I hat dotted with I hat times dx, and I'm going to go from x equals 0 to 1, and that's going to give me, of course, I hat dot I hat is just 1, because it's 1 times 1, that's the magnitude of each of those, times the cosine of the angle between them, which is 0 degrees. So that's just plain 1. So the integral of 4x dx becomes 2x squared from x equals 0 to 1. That's going to become 2 times 1 squared minus 2 times 0 squared, which is just equal to 2.00. Notice that that 2 there should have units of newtons per meter. And then the x squared would have units of meters. So this is newtons times meters, which is a joule. So I'm getting 2.00 joules for that. And I'm trying to double check right now to see if that's the answer. Yes, and that's the answer they have is 2.00 joules. Oh my gosh. Sorry, I covered up the window while I was looking at, so I didn't even see that. Let me share my screen again, Diana. I'm very sorry. That was idiotic of me. Here you go. I'm sitting here talking to a screen that's not there. Such a crackhead. Okay. Sorry again. Here you go. So this is what I worked out. It might actually be a little bit easier for me to explain it to you. So the force, as you can see up at the top, was the 4 newtons per meter times x I hat, and then 2.00 newtons per meter squared times xy. Notice that's what the units have to be, because obviously x and y are normally measured in meters. So if you multiply 4.00 times x in meters, then you still need the force to come out in units of Newton. So that 4 has to be newtons per meter, just so it'll cancel out the meter and the x. Similarly, that 2 has to be newtons per meter squared, just so it'll cancel out the meter and the x and the meter and the y. So that's why that worked out. What I told you is we were calculating the work W from the initial position, which is 0, 0, to the final position, which is 1.00 meters, 0.00 meters. Now, if this is a conservative force, and they really should have to either tell you exactly what path they're choosing, or they really should let you know that it's a conservative force. But the main thing is you can't do this at all unless, 1, they give you the path, or 2, you make the assumption or they tell you that the force is conservative, because then the work is independent of path. So that's what I'm doing. I'm assuming the work is independent of path, and I draw the path to be a horizontal line. Notice the blue line on the x and y axes there. It's a horizontal line from the origin to x equals 0, x equals 1, y equals 0. So that's that final point. And I just drew it with a blue arrow, and then I imagined at an arbitrary position x, which goes from here to say here, that's x. And then what I'm also saying is this right here is the distance dx. So we can make the argument that obviously the DL, a differential tangent vector, that's really what the DL is, supposed to be a vector that's sort of tangent to the path at each point. Obviously, tangent to the path means parallel, so it should actually point in the I hat direction. So clearly DL is dx I hat. That works. Now I put that in, work equals the integral of f dot dl, which was this equation right here. Okay. Now, for it to really be on the path, you need to evaluate x's and y's along that path. Now, along that path, y was equal 0, so I really had to substitute y equal to 0 in there, and that's why that is 0. Now, the dot product, you can actually treat, remember this dot product is a linear operator. So what's really happening is I'm taking 4x I hat plus 0 j hat, and I'm dotting that with dx I hat. What you can do is you can say, okay, well, let's let the 4x times the dx. In other words, I put all the scalars out in front, and now I'm going to say I hat dot I hat. That's like the distributive property where I just let this one hit. Now I've got to use the distributive property again to let this one hit. In that case, I'm going to get plus 0 times dx times j hat dot I hat. Of course, j hat dot I hat is 0. So I end up getting just 4x times I hat dot I hat. The magnitude of I hat is 1. The magnitude of the other I hat is 1. The angle between them is 0. So it's times cosine 0. So clearly that is just times 1. So the integral just becomes 4x times dx. That's what I'm showing right here. I integrate that from x equals 0 to 1. And the integral of 4x is in fact 2x squared, because basically the integral of x dx is 1/2 x squared plus a constant. So that 1/2 multiplied by the 4 gives me the 2, which is why that's there. And then I evaluate, turns out to be 2.00 Newton meters, which is the same thing as a joule. Did that help you, Diana? I'm trying to look at the chat now. There it is. Gotcha. Any other questions then? By all means, I haven't graded it yet. Go back, figure out how to do that problem and turn it in with your other, with the rest of your pages. And if you get it in there before I grade it, then you'll still get credit for doing all of them. So if you did it somewhat similar, that's a good thing, Diana. The main thing is, yeah, this is something that line integrals and path integrals are something that's not normally not even covered till Calc 3, if they're gotten to at all. So it's perfectly reasonable for you to not know that. However, I have been trying to teach you guys, so you'll use it a lot more next semester. But you're welcome. Have a good evening, and I will see you at next class.